Chapter 6 is going to be very, very different from anything we've done before. And it's going to be an interesting challenge to do this from distance. So no matter what, I know we will start Chapter 6 in this strange format of me talking to an iPad and writing on it, and you watching the video in Classroom via YouTube. Hopefully we get back to seeing each other face to face long before we get towards the end of the chapter. So we're going to be talking about systems of equations, which means we're going to be looking at multiple equations at the same time. Okay, so vocabulary. System of linear equations is a set of two or more linear equations containing two or more variables. Okay. For us, it's going to be two equations, two variables, x and y. The solution of a system is an ordered pair, so an xy ordered pair, that satisfies, meaning make true, both equations in the system. So in section 1, we're going to test ordered pairs to see if they are solutions, and we are going to graph equations to see where their solution point is. Up first is determining if an ordered pair is a solution. So in the first example here, I have the ordered pair 4, 1, and I'm given two different equations. What we're going to do is take those equations and plug 4 in for x, 1 in for y, and see what happens. So in the first equation, we have x plus 2y equals 6. We're putting in 4 for x and 1 for y, so we're going to have 2 times 1. And the question is this true? Well, 2 times 1 is 2, and 4 plus 2 is indeed 6. Obviously, I'm going to use more space here than you should if you are printing. I will have to erase to do the next example. So 4, 1 satisfies the first equation. We're good. We move on to see if it satisfies the second. So the second equation is x minus 3y is equal to 3. I'm going to put 4 in for x. I'm going to put 1 in for y. And the question is this true? And pretty quickly, I think we can see it's not. 3 times 1 is 3. And 4 minus 3 is 1. 1 is not equal to 3. So, no, 4, 1 is not a solution to this system because it doesn't work in both equations. Okay? When you're doing your practice problems in your assignment, if you're checking an ordered pair, you need 2 yeses in order to say that it works. If you have a single no, you can stop working. The answer is no. So to test that theory, and make sure we know what we're doing, we're going to do the same thing we just did, but now in the second example. So my first equation is 2x plus 5y equals 8. This time my ordered pair is negative 1, 2. So I'm going to be putting negative 1 in for x, and I'm going to be putting 2 in for y. Do our multiplication. 2 times negative 1 is negative 2. 5 times 2 is 10. And negative 2 plus 10 is indeed 8. So our first equation works. Let's check our second equation. 3x minus 2y equals 5. Again, we are substituting negative 1 in for x, and we are substituting 2 in for y. Three times negative 1 is negative 3. Negative 2 times 2 is negative 4. And negative 3 minus 4 is negative 7. Negative 7 is not 5. So again, no. I know it's a little strange that I'm giving you two examples that both go no. Okay? Just realize to say yes, an ordered pair is a solution, we must have both ordered pairs, or sorry, the ordered pair working in both equations. Now, if we graph a system of equations, its solution will be the point where the lines intersect. This is going to be really difficult for me to do, so bear with me. Solve these equations by graphing. So the first example here, we have y equals x plus 3 and y equals negative x minus 1. Those are both in slope-intercept form. Okay, so we can graph them straight off. X plus 3, and I'm actually going to do these with different colors so they stand out. So x plus 3, we start at positive 3. Again, this is going to be very difficult for me to do. The number with x is an invisible 1, so that means up 1, right 1. Up 1, right 1. Up 1, right 1, and so on and so on. Unfortunately, I am not going to be able to draw this on the iPad. The definition I would need is just too small. Let's see if I can maybe get lucky if I blow this up a bit. So let me try this one more time. X plus 3. We start at positive 3. Can I have just a bigger dot? Let's see if... Plonk. There we go. Up 1, right 1. Up 1, right 1. Now, in the past, we would just do one extra dot. I'm going to strongly recommend that you continue this pattern all the way to the edge of the grid, and then turn around and reverse it. Okay, you should see if we were going up 1, right 1, reversing that would be down 1, left 1. And again, I would strongly encourage you to extend that all the way to the edge of the grid. I'm doing the best I can here. It's not the nicest. And of course, we would connect those with a line. So let me thin that back up and do a really poor job of drawing a line. Use a roller, you know. Okay. So let's use blue. Blue will jump out against that, and big points again. So the next line is y equals negative x minus 1. Y-intercept is minus 1, so I put a point there. And the slope, the number with x, is negative 1, which means down 1, right 1. Down 1, right 1, down 1, right 1. And we keep on going, because like I said, I want you to go to the edge. And then reverse. Instead of down, right, I'm going to go up, left. I should have a point where they match. The blue and the red lines match. Okay. And here, that point is there. It is the ordered pair negative 2, 1. I would strongly recommend that you practice doing these by hand, so long as we are back doing face-to-face classes before the quiz on 6-1 to 6-4, which is like the middle of April. You will have to do these by hand. However, since we're doing distance learning and we can use technology a little bit more, I'm going to show you something. So the next example is x plus y equals 0 and y equals 1/2 x plus 1. What we can do is go off here and find Desmos, our graphing calculator, and let it do the heavy lifting for us. Okay. So we have x plus y equals 0. So x plus y equals 0. There's a line. And we also have y equals negative 1/2 x plus 1. y equals -1/2 x, got to get the x out of the denominator, plus 1. And you can see as soon as we put that in, it's showing us a couple of different points. We care about the point where they intersect. And if you tap the screen, it'll tell you exactly where that is. So the solution to the second example is -2, 2. Okay. Now let me be clear on this. While you're at home, do I mind you using Desmos to check your work? Absolutely not. Can I stop you from using it to do all your work? Again, no, I can't. But when we come back, I'm not going to take a lot of time to go over how to graph these lines. So you need to keep on top of this, guys. Otherwise, when we come back, life's going to hurt a little bit. We will deal with word problems. So, Bolorama charges $2.50 a game plus $2 for shoe rental. And Bowling Pins charges $2 a game plus $4 for rental. What we need to do is find out how many games would we match up. So how many games do I have to bullet each so that I spend the exact same amount of money? And I've got here 3 steps. Step 1, write a function in slope-intercept form for each bowling alley. Okay. So Bolorama. My cost, which will be y, is equal to $2.50 for each game that I bowl, so 250x, plus $2 for shoe rental. Bowling Pins, actually let me change colors here. Bowling Pins the total cost for these guys is going to be $2 a game, so 2x, plus the $4 shoe rental. I want to know when these are the same. Okay. Again, we should graph. Okay. Going to point something out here. We're spending money and we're bowling. You aren't going to spend negative money and you can't bowl a negative number of games. So if I'm doing this, then in terms of this grid here, like all of this, I wouldn't need or want to consider. I would only want to focus all of my energy in graphing these equations here in quadrant 1. If you're going to do that, we should probably do a quick conversion of 250 250 is actually 5/2 x plus 2. That could be useful to have. Okay, so write a function in slope-intercept form. We did that. Graph. I'm going to leave you to do that. I'm going to pop over to Desmos and do it. So we're going to get rid of all of that. And I'm going to get rid of all of that. So the first bowling alley was $2.50 a game plus a $2 shoe rental. So there he is. And my other bowling alley was $2 a game, but they charged you $4 for each shoe. So where do those meet? 412. Pop back over here, make a quick note of that. 412. Okay. If you were listening when I was talking earlier, I kept saying y is the cost and x is the number of games. So how many games will the cost to bowl at each location be the same? 4. And what is the cost? $12.